Hey everyone, welcome to this latest installment of the International Postdoc Series hosted by the Minnesota Center for Philosophy of Science. My name is Max Drazo. I am a postdoc here at the center. I'm filling in today for Alan Love, the center director who's traveling and couldn't be here. So it's my pleasure to introduce William Peden, who comes to us from Erasmus University, Rotterdam. William did his PhD at Durham, and he's going to be speaking today about the statistics wars, so named by Deborah Mayo. So this is how this is going to work. William is going to give his talk. That'll take about 45 minutes. After that, we'll hand it over to Samuel Fletcher, professor of philosophy at the University of Minnesota, who will give a short commentary, about 10 minutes or so, on the talk. And then after that, there'll be an open Q&A lasting about half an hour. So we'll finish up around 1:45. If you have questions during the talk, feel free to drop them in the Q&A, and I'll be monitoring that. And also, if things come up after the commentary, things like I'll be monitoring it in real time as we go along. So I am going to hand it off to William to talk about peace in the statistics wars.
Thank you very much, Max. Just share my screen. Thank you very much, and thank you very much for inviting me. It's been a tremendous opportunity to present at such an important place for philosophy of science, where a lot of interesting work has been done, especially with respect to the philosophy of statistics. This is primarily based on a joint paper with Mantas Radvilas and Francesco Di Pretis. We are also working on a further paper developing some ideas from this study, and that's also an exciting opportunity because the feedback from this session we can really use in that paper, which is wonderful. Now, the phrase of the statistics wars we take from Deborah Mayo, who has, I think, done a tremendous amount to clarify some of the differences and similarities between statistical methodologies. Now, one of the challenges here with understanding this debate within the philosophy of statistics is that there are so many different questions, and there can be a number of very assorted and variegated answers to these questions. So at the, say, evaluative level, we can ask, well, what are the proper criteria for assessing statistical tests and their results? We can also ask at the level of practice, under different sorts of conditions, different sorts of scientific problems, which statistical tests should we perform? And then finally, at the institutional level, we can ask, well, what type of studies should we be publishing, and what should these studies report about the statistical data and tests that they perform? And these questions, which are obviously all at the heart of scientific practice, depend on our answers to various methodological questions. So one point of view here is called frequentism, sometimes also called classical statistics. And there are really two main pathways to this view. And I want to mention both, particularly in honor to Deborah Mayo. So one route, which is quite traditional within frequentist statistics, is through the idea of evaluating tests by looking at their long-run performance properties, and then which is to essentially ask a hypothetical question: if we repeated this type of test in the long run as approaching infinity, how would it perform? Another way of putting that is, how would it perform in the limit? And with certain frequentist methods, such as confidence intervals, we can prove that given certain initial conditions, these are going to make an arbitrarily small degree of error in the long run in the limit. You can come to the same ideas, or very similar ideas, through the idea of severe testing. And here the idea, very informally, is, would the evidence be surprising if the tested hypothesis were false? And this view has been particularly clarified by Mayo, who has made the case that it avoids some of the problems with the performance path of frequentism. Now, these are very related views because obviously, for example, the long run performance is relevant for the severity of a test. But there are also other issues of methodology, like, is a study going to be replicated? How is the study designed? How is the data collected? Which are perhaps a bit easier to justify measures to deal with these from a severity point of view. The other view, based on a theorem of the probability calculus from Thomas Bayes that is almost literally being idolized, this is a neon sign somewhere, is the idea of Bayesian statistics. Here the idea is to take a probability distribution, determine the conditional probabilities of different elements of that probability distribution, normally something like propositions or maybe statements, and then update this, adopt a new probability distribution on some evidence by setting the probability of that evidence to 1 in the new distribution, and then setting the probability of your hypothesis to its previous conditional probability relative to your evidence. Actually, within Bayesian statistics, one of the means of actually assessing the evidential support for some statistical model, let's say, is by using the likelihoods of the data given that model and another model to get a sort of comparative measure of evidential support. And that's called Bayes factors. A final note on Bayesianism is that Bayesians and frequentists typically use the term probability in different ways. Frequentists typically interpret it in terms of the relative frequency of one event to another. Bayesians tend to interpret it as a measure of degree of belief. But these divisions are not very sharp. You can give justifications of frequentist statistics using the types of interpretation of probability that Bayesians tend to prefer. So there's been work on quite a while ago now by Henry Keiberg on that, and more recently by John Williamson. So I don't want to suggest that the lines here are sharp at all, either methodologically or philosophically. So there is often quite a heated dispute among practicing statisticians who lean more or less more towards one side or another. But since it is a methodological dispute, that raises the question, how can we actually resolve this? It's not something that lends itself, obviously, towards standard scientific methods for deciding who is right or who is wrong. Now, there's a lot of formal work done on these two theories, and you can find various things about them from a formal point of view that is very good. It's hard to say from these proofs which side is better. There's been a lot of debate about that going back for 150 years or more. Many a statistician and many a practicing scientist and many a philosopher would say, well, it depends on the context. What we should use, which approach we should take, is whatever works in this particular context. And from the point of view of common sense, that's very attractive. But how do we find out what works in particular contexts? If you use historical case studies, you're going to have very small samples and be vulnerable to random error. If you put them together, collate them, you can often be combining very different historical episodes in the history of statistics and thus be vulnerable to systematic error. You could then say, well, what we need is some sort of meta methodology or a hybrid view, something that will tell us which approach to adopt in which context from a more sort of a priori angle. And I'm very sympathetic towards that idea, but it does raise the question, of course, how can we justify that theory? And that's also a big challenge. But one thing that both Bayesians and frequentists want us to do is to guide us towards good decisions. So Bishop Butler famously said that probability is the very guide to life. And we could also say that we want statistics to be a good guide to our lives. Again, here there are some good formal proofs on both sides. We can prove that in the long run, in the hypothetical limit, both methodologies have some very attractive features. Both of them are going to, under the right conditions, lead us to very well-founded decisions. One alternative route then is to look at the short run, what happens not in that hypothetical limit, but within much shorter time spans. And here, a method that's become quite popular in recent philosophy can really help. And these are simulations. Simulations enable us to study the evolution of a process. And this can provide useful information even if we know what's going to happen in the limit. So for example, in economics, we might be able to determine that there are good net benefits for a policy in the long run. But if there are costs in the short run and in any sort of conceivable time span, the policy is not going to be beneficial, that's not an attractive policy because, for one thing, politicians are not going to stick to that. On the short run and the long run, Keynes is famous for saying, the economist John Maynard Keynes is famous for saying something that's often misinterpreted, which is, in the long run, we're all dead. Much earlier than that, he said something which is, I think, much clearer, makes the same point in a much better way, which was to say that economists set themselves too easy a task if, in tempestuous seasons, they can only tell us that when the storm is long past, the ocean is flat again. So what happens in the long run can be important, but the route to that long run is also something we care about. And potentially this is one way where we can get a good idea of which approaches work in which sorts of context. So to study this, we developed a simulation based around a decision problem, and we coded 4 different players representing, or three of which represent views within the statistics wars. One of these is a standard Bayesian. The other is a view based on, I'm going to explain in a bit more detail later, but is a particular kind of Bayesian that represents a kind of hybrid position within the statistics wars, a sort of middle ground maybe, and a frequentist player. And then finally, a benchmark player whose performance we use as a comparison for the other player. And that benchmark player uses a very sort of simplistic, naive version of induction. Three of these four players had a lot of variety in their settings. And as a result, in practice, we had to do quite a lot of simulations to evaluate each different setting of the players. And the decision problem that the players face is to make bets on a sequence of events, each of which has two possible outcomes, what's normally called a binomial event. Now, we use the language of coin tosses to talk about this, but that can be a bit misleading because we know quite a lot about coin tosses in the real world, a lot more than our players know. Therefore, one other way to think about our problem, if you find it sort of hard to imagine being ignorant about coin tosses, is this three-dimensional solid here called a gombok, which is a very interesting shape. It was discovered only about 30 years ago mathematically and made even more recently in the real world. I won't tell you what the dynamics of this physics are, but I'll just say that they are very interesting. And if you were to toss a gombok, you might notice some regularities that puzzle you. So our players are ignorant about the tendencies of the events they are observing. Coin tosses, if we think of them that way, could be biased anywhere in the unit interval towards one result or the other. So the coin could be very, very biased towards heads, could be very, very biased towards tails, could be fair, could be all sorts of things. And those were the events that they were betting on. And then to determine the bets themselves, we randomly generated ticket prices for the bets, betting on either heads or tails. We stored these so that the players had the same observations to deal with, and they had the same ticket prices. So essentially they're facing the same decision problem. And they had three possible actions that they could do. They could choose to hold as well, so that they could bet on heads, they could bet on tails, they could choose to hold, to not bet. But the way the players work, only one type of player, the frequentist player, would ever choose this option. So for some simulations, we controlled for this option by eliminating it. And we didn't find that when the frequentist player didn't have the option to hold, we didn't find any difference from when they did have the option to hold. Nothing we could detect anyway. Okay, and then for the actual observations the players were given, we gave them cumulative sets of 5 observations of tosses. Now in each of these sets, firstly, they saw 4 new observations. They didn't see the 5th observation, and then they had the opportunity to buy a heads ticket, tails ticket, or neither on the 5th toss. So it's the 5th toss they were betting on. But just to stress that, so in the first part of the simulation, the first game within the simulation, they would be observing just 4 tosses. They would then add the 5th toss once the bet on that had been resolved, add that to their evidence, and then over the sets, their number of observations would increase linearly. We also tried the same thing with sets of 10 tosses, and we had fundamentally the same results. Again, we couldn't detect any differences, but I'll just be referring to the results with 5 observations today. We also varied the coin biases. So the players didn't know these biases, and they didn't know that these were the only possible coin biases that we were investigating. But they did know that the coin tosses were exchangeable, and this means that they knew that the order of the coin tosses was irrelevant. So if they got heads, tails, heads, they would treat that as the same evidence as if they got some series like 3 heads and then 2 tails. So the 5 coin biases that we looked at with respect to heads were 0.1, 0.3, 0.5, and 0.9. So cutting up the range of possible coin biases that way. We then did 1,000 simulations per bias, and then 1,000 gains per simulation to reduce random error. We ended up doing quite a lot of simulations, as it happens. So we ended up with over 50,000 of them, which works out to 100 million games, each of them with, I suppose, 5 or 10 coin tosses. Thank goodness we didn't have to do this study in the real world. Otherwise, our wrists would have got very tired tossing those coin tosses millions of times. Thank goodness for computers. Okay, so I mentioned earlier that we had a benchmark player called the sample player. Well, we call them the sample player. And the idea here, which we took from an earlier study, was that if a statistical methodology is worth using, then it should at least match crude induction. The sample player just infers that the probability of heads is the frequency in the sample of heads they've observed so far. Then, given that probability, and given their knowledge of the ticket prices, they make a decision that maximizes their expected payoff given the probability. Just briefly note, we're talking about payoffs here rather than utilities, but that's a small detail. But if you're familiar with maximizing expected utility, it's the same idea. It's just the quantity you're using instead of utility is the payoffs in the game, the monetary payoff. And the benchmark we set using this player was if we estimate the range of players' performances using a 0.95 confidence interval. So we estimate boundaries for the random error using of players' performances using that. Is it equal or greater to samples' use of naive induction? So in other words, well, I can go into more detail of that if you want, but that was how we used sample player as a benchmark. The Bayesian made the same decisions, or made decisions in the same way as the sample player. So they're also maximizing their expected payoffs using their posterior probabilities. So those are the probabilities that the Bayesian has after observing some data. But as you may know, with Bayesianism, what determines the posterior probability is not just the samples you observe, but also the initial probability distribution, or also known as the prior. There are lots of different kinds of prior that the Bayesian could use for the decision problem we looked at. But the sort of textbook answer, a very popular answer we think among Bayesian statisticians, would be to use what's called a beta distribution. And a beta distribution essentially tells you what your credences should be for each possible coin bias and conditional probabilities. It also gives you conditional probabilities for each toss. So it gives all the Bayesian all they need to make decisions, and in a fairly sophisticated way. They're not just thinking about the next toss, they're thinking, in a sense, about the coin biases in general. beta distributions are popular partly because they are very convenient for specifying lots of different types of prior. So beta distributions are a family of prior, and they can be characterized using just two hyperparameters. Hyperparameters are parameters characterizing different prior probability distributions. So if you think about the relative frequencies of some event, well, there we can characterize that in terms of the mean and the standard deviation and other parameters. Hyperparameters, just the same idea, but applied to a probability distribution, a prior probability distribution. And we characterize these with one favoring heads, one favoring tails, and Bayesians updating basically meant going from one beta distribution to another. What the hyperparameters let you do is, well, one of the things we can get them to do is, if we set their values high, we can create a prior that's tougher in the sense of being less responsive to evidence. And some of you might have heard of something called objective Bayesianism. In this context, objective Bayesians would normally go for values for A and B of 1, 1. Essentially what that does is gives the same value to each of those, gives the same strength to each of those, but also gives a low strength because a beta distribution can have any value greater than 0 and then up towards infinity, basically. And just to give a quick visual illustration, setting different values for the two parts of the beta distribution shifts the probability densities for the event. This is actually not the complete expressive power, which I couldn't show with an animation even in principle. But just to walk through a few of these probability densities, one that we look at is a beta distribution that's biased towards heads. And so this puts all of the probability mass towards one side of the distribution, towards heads. Now, note here that the y-axis is different. The flat prior, which is what an objective Bayesian would normally favor, has this shape, distributes the probability density evenly. Tails, exactly symmetric with pro-heads. So we looked at these three probability distributions for the Bayesian, but there are other options. So for example, you can have a prior that's equivocal between heads and tails, but is very unresponsive to evidence. You can have Jeffrey's prior, which is another kind of symmetrical prior. And you can also have a prior that's biased, but more responsive to evidence. Okay, so now to get on to the results of our simulations. So what I have here are charts which will show you the average for players minus the average for players, average payoffs for the players minus the average for the sample player, our benchmark player. And this is the Bayesian with a prior that's biased towards heads. And each of these colors represents a different bias for the coin. And one other thing to note here on the, so on the x-axis, note that these values are not increasing linearly. And also with the y-axis, these are the differences in payoff, in average payoff. And the highest, these would be 1, so it's in the unit interval. Okay, the results for the Bayesian that was biased towards heads were, in a sense, quite predictable. So if the coin is not biased towards heads and very strongly biased towards tails, then being biased towards heads was a big problem. But interestingly, there wasn't a massive gain over the sample player, even when the heads player's bias was in the right sort of ballpark. And in fact, this difference here is not statistically significant at all. So this kind of Bayesian is, in a sense, taking a big risk if they've got the prior wrong, but also they're not really getting anything out of having that bias. On the other hand, with the flat prior Bayesian, they consistently outperformed the sample player. Not a massive difference, but at the very least, they were always doing about as well or better than the sample player. So, and this type of Bayesian is very responsive to evidence, and they did very well. Just another note, don't overinterpret small differences here, basically. So for example, the fact that this type of Bayesian, it seems to be doing better with a bias towards 0.3 than towards 0.7, say, that's not really important. In fact, the y-axis of the chart here is different, and these are very small differences. Okay, for the frequentist player, we did face the challenge of choosing an estimation method for them. Again, we thought that a popular choice among frequentists would be confidence interval estimation. Confidence interval estimation involves setting a confidence level, which essentially measures the level of long-run error that you're willing to tolerate in your estimations. And the point here is then that your estimates, if you estimate that the true bias is going to be somewhere in a certain interval, then with confidence interval estimation, then in the long run, your error is not going to be greater than the confidence level. So level is putting, in a sense, a minimum lower bound for long run error. The frequentist, so then, estimates initial boundaries, and then with their initial sample of coin toss observations, and then updates these as updates this interval as their data increases. Choosing a decision rule was also a challenge here. We chose one that is a very weak decision rule. It is not very informative, but is at least something that frequentists would tend to agree with insofar as it goes. And this is to choose one of the actions that isn't dominated given your confidence interval and the ticket price in that particular game. Domination here means that if you know that some action is going to be worse than some other action, given that the coin toss is anywhere in that interval, then the action is dominated and it's not really rational to do that action. And here I have a picture of Egon Persson, who was an important figure in developing confidence interval estimation. Rather to our surprise, the frequentists didn't do well with the standard sorts of confidence levels. This is not a terrible performance here towards the beginning, and the frequentist certainly catches up at a perfectly respectable rate, but it is, and it's nowhere near as bad as the Bayesian, who is biased towards heads, but nonetheless, it was not one of the top performing players with this setting. On the other hand, with a more unusual sort of confidence level, the frequentist did very well and not detectably different from the objective Bayesian, who is another high-performing player. So the frequentist with the right setting could do very well and pass the benchmark very convincingly. Now, the final methodology, which I'm going to have to skim through quite quickly, unfortunately, functions as a hybrid player, using a Bayesian interpretation of probability, but in many contexts, such as this one, using frequentist statistics. And this approach has been developed by John Williamson of the University of Kent. In his methodology, you first use frequentist methods to narrow down the range of possible Bayesian probability distributions you might choose in this sort of context where your background knowledge doesn't give you a frequency-based prior. And then you choose the probability distribution that provides minimal information or equivocates about the fundamental possibilities, which here are heads and tails. And in this context, the Williamsonian player is going to use a confidence interval, and then they will pick a Bayesian probability that is as close as possible to 0.5. And just to very quickly illustrate that, so subjective Bayesian might choose anywhere for their bias, anywhere in the unit interval for their probability. Williamsonian, if they can, is going to pick 0.5. And in other words, if 0.5 is in the confidence interval for the coin bias, but if 0.5 is not in the confidence interval for the coin bias, given their estimation, they will choose the closest value to 0.5. So here it would be 0.9 with a confidence interval of 0.9 to 1. To cut a long story short, the Williamsonian player was very parallel to the frequentist player. They did well with this curiously low confidence level. But with a low confidence level, the Williamsonian matched the flat prior Bayesian, the frequentist with the best settings for frequentists, and the sample player. So the differences here are very marginal in the short run, and then in the long run, as the number of gains increase and their data increases, the differences between the players' average payoffs become non-notable. This is with the toughest possible setting of a 0.5 coin bias. That's the type of setting for the coin bias that's most difficult for players, for reasons I can explain if you want. And then for the worst performing player, just to give a comparison, was actually the Bayesian who was biased towards tails. That's probably just a random thing between that and being biased towards heads, but they were doing a lot worse. So the key take-home message here is that players with their optimal settings could do very well, but with a bias prior, Bayesians could do very badly. Okay, so what are the take-homes from our study? Well, unlike a similar study, we didn't find that the frequentist had any generally superior performance relative to the Bayesian player. And we can explain this difference because they used a much smaller sample of simulations, 100 simulations per setting, and their study would have much higher random error than ours. The players performed well with suitable settings, as you saw. The interesting thing here is that for objective Bayesian, that flat prior is mandatory. For Williamsonians and subjective Bayesians, the settings that worked well for their respective players are optional. And then finally, for frequentists, as I've mentioned, the best performing setting is not normally used, but is actually perfectly consistent with frequentist statistics. This is purely speculative, but it's possible that in some decision-making problems, frequentists might face a trade-off between reliable inference, as measured by high confidence levels, and decision-making performance. And this would be something very interesting to look into in the future. Another take-home message is that, in my experience and the experience of my co-authors, and maybe your experience as well, some Bayesians are very relaxed about priors. They say, well, in the long run, it really doesn't matter. But they shouldn't be, because in the short run, it really does make a very big difference. And these were by no means the worst type of priors that we selected. We could easily choose priors that did very, very, very badly. Williamsonianism has had some attention in philosophy, but the vast majority of practicing statisticians are unfamiliar with it. And I hope that our study will provide at least some statisticians with some motivation to take a look at it. I think it could have interesting applications. And then finally, methodologically, we have a research program here that we at least are very excited about, because we can code any clear statistical methodology that philosophers or statisticians come up with into players, create some decision problems where we can't predict who is going to win, and then contrast them. This time we kept things really quite simple, and there are a lot of limitations that result from that. Partly to test what is possible, and then also so we could have good comparisons with earlier research. As I mentioned, there are limitations. Here are just a few of them. So we only looked at one decision problem. This problem had the advantage that it's a sort of textbook statistical problem where we could take off-the-shelf solutions from the methodologies, but maybe one or more methodology would do worse with a more complex decision problem. We used a benchmark player, which is not the best way to do this. And we're looking forward to using more sophisticated comparisons in the future. Players in this game, they can never go broke. There's in a sense like they have infinite amount of money. But in real world decision making, this is an important factor. So we want to incorporate that into our future simulations. Relatedly, real world decisions involve Matthew effects. So our players could always bet up to the same amount, but in the real world, alas, the more you have, the more it's easier in many contexts to get more. So, and that gives an advantage to good performance in the very short run. And one other problem is that our players differ both in their statistical methodologies and their decision rules. These are closely related, but they are distinct. So it'll be interesting to determine to what extent these performances due to how they revise their beliefs, their methodology, and to what extent are they due to the decision rules that they use. So we're working on a new simulation where, for example, we will track when players would run out of an initial sum of money. We're also using imprecise probabilities, which is an approach to probability that's had a lot of interest in philosophy recently, for example, by Richard Bradley in his recent book. Imprecise probabilities, and particularly imprecise probability decision rules, what these enable us to do is actually control for the effects of the decision rule. So we can compare Bayesians and frequentists using the same decision rule, which addresses one of the confounders in this study I've described. So finally, I'd like to thank my co-authors, Mantis Radvilas and Francesco Di Pretis. I'd also like to thank Daniele Tortoli, who has provided tremendous technical support for this study and enabled us to achieve some computational things that we could have never guessed were possible at the beginning. And finally, I'd like to thank you for listening, and I look forward to talking with you a lot more about this. Thank you very much.
Thanks, William. That was really interesting stuff. We're going to hand it over now to Sam Fletcher for a brief commentary. And just to remind you, if you have questions, please drop them in the Q&A at any time.
Great. Wonderful. Thanks so much, William, for this presentation on your work with your co-authors. The first thing that I'd like to do in my commentary is to actually give some congratulations for the work well done. Simulation work of this caliber, especially in philosophy, is not easy, but it should be incentivized and there should be more of it. So I, in particular, hope that William and his co-authors will post their data and code in an online repository so that folks who are interested in checking out the work and doing variations on it will be able to do so by building upon their work rather than having to work it afresh. And also doing so will help contribute to the reproducibility of this little simulation neighborhood of philosophy of statistics. I think, though, in the interest of promoting a broad discussion, I'm going to focus on some points of disagreement. So one interesting thing, actually, we can already see in the difference in the way that William framed the work in the presentation and the way that it's framed in the published paper. This difference between whether or not this is a sort of means of making peace or whether this is just another battle in the statistics wars. I think we have some reasons for skepticism that this sort of work will contribute much to peace, at least from the perspective of the frequentist or the classical statistician. There's a lot to say about all these different positions, but I'm just going to focus on that position in the interest of time. I'm going to focus on three different types of issues that I think will make it so that it's not clear how this sort of work is going to contribute to a mutual peace between these different statistical methodologies. The first problem that I'll talk about is how representative this decision problem that is used in the simulation is really representative of the sorts of problems that classical statistics aims to try to solve. The second has to do with this unusual result that a kind of setting for frequentist inference that's usually considered weird or unreliable seems to be good for decision making, and how we should understand that contrast and whether it is a something that contributes to peace or not between different methodologies. And the third is a kind of more general methodological issue about the role of instrumental criteria in evaluating statistical methodologies. Instrumental criteria, that is about kind of like how much money you're going to make in a decision problem over time. Okay, so maybe it's worthwhile briefly just to talk a little bit about different viewpoints within classical statistics. There are a lot of important figures historically, but two central ones are Ronald Fisher and Jerzy Neyman. Now, both of these folks had overlapping ideas about the nature of statistical inference and statistical testing, and the kind of disputes between them over time tended to amplify those differences. So there's a kind of perspective that's sometimes called inductive inference that's associated with Fisher, and a different sort called inductive behavior that's associated with Neyman. The idea with inductive inference is that you're supposed to somehow use data to make inferences about ways the world could be. You use the data in order to try to, in philosophical terms, confirm or disconfirm hypotheses of interest. And so the inferences that you make are about hypotheses that you're ruling out, hypotheses that are supported by the data. For Neyman, the view of inductive behavior is that statistics is not a tool for making, as it were, inferences about the nature of the world, but as a guide for making decisions that in the long run will have certain desirable properties. The sort of situation that's often used to describe this sort of viewpoint is a situation where one is in charge of quality control in a factory. And you want to have some sort of decision procedure for ensuring that as often as you can, you reject parts that are made in the factory that are defective, and you accept parts that are not defective. Now, it's very easy to do one or the other. To always accept all the good parts, you could just never reject any. To always reject the bad parts, you can reject all the parts, but you need to have some sort of balance between the two. And coming up with a balance prescribes a particular rule for how one makes, how one does statistical testing. Now, in both of these sorts of different approaches to classical statistics, they're focused either on the one hand, inferences about the nature of the world, hypotheses, or they are procedures for, on average, doing the best you can, getting the most proportion of a certain cases that you want to evaluate right, where the level of rightness is going to depend on the costs for getting a certain type of case right or wrong. Think again of the case of the factory producing widgets. Getting it wrong would be rejecting a part that's acceptable, or not rejecting a part that's defective. Now, when we look at these sorts of things, these different kinds of attitudes or problems that we use to address, we use classical statistics to address, they just don't really fit well with the sort of problem that William and his colleagues are considering. They're not about individual decision-making to minimize financial loss in a sort of betting game. So they're not inductive inference. The goal is not to find the best evidence about the bias, to come to conclusions about the bias. It's not inductive behavior either, because the goal isn't to make the correct decision about what the bias is a certain fraction of the time. The goal is to maximize long-run profit, or on average, or something like that. Now, the problem is related to, but it's distinct from, a problem of prediction. So these sorts of tools here, these are supposed to be inferences or behavior about the bias of the coin, rather than about what the next coin toss is going to be. And that is, and what the next coin toss is going to be, combined with potential bets that the player could use, or the things that William and colleagues are using to evaluate these different methodologies. For this, probably a better tool would be prediction intervals rather than confidence intervals, because they take into account extra uncertainty that's associated with prediction, and one wants to make an inference to the next observation rather than a parameter that's specifying a way the world could be. The next thing I wanted to talk about is this, whether it's good to be weird and unreliable. So one of the things that William mentioned is that to be competitive at this game, the frequentist needs to adopt a very low confidence interval, almost the opposite of what we usually want in inference. I think the reason for this has to do with an artifact of the imposed decision rule. When one has low confidence level, that tends to prescribe a narrower confidence interval, and therefore determine less randomized choices for the frequentist player, based on the decision rule that if they don't have a choice that dominates, they randomize amongst the ones that don't. This diagram here is just an example to remind you, from an example of a normal distribution, how it is that lower confidence intervals tend to lead to narrower intervals. Here, right, we have an interval that has a very high confidence level. Here we have one that has an even lower one. Here we have one that's even lower. And as you can see, as the confidence level gets lower and lower, the interval shrinks down and down and down. It seems to me that, therefore, that the reason for this has to do with this particular decision rule. And I think it again illustrates how the particular decision problem that's being used to evaluate these different statistical methodologies is rather different from what classical statistics is really designed for. Let me at last come to whether or not we should be using instrumental criteria to rate methodologies at all. The problem that we face is pretty familiar. We have a bunch of methodologies that seem like they're doing very different things. It seems like they have different goals. They're totally at odds at what they aim it's very natural or tempting to find some criteria into which you can embed all the different things, a task that you can evaluate them all, so you can rate them. The problem, though, is that this particular task is maybe better suited to some of these methodologies than others. Bayesian methodologies tend to be better aligned with goals of individual decision-making. And so the kind of task that it's being asked to do there fits better with that sort of approach to inference and testing. If we have to add a decision rule also to the methodology, then the rating, and William did emphasize this at one point, has as much to do with the added decision rule as it does to have to do with the methodology. It would be helpful to try to find a way to try to separate these two if we really want to evaluate methodologies, and not methodologies plus decision rules that are not determined by them. That's all to say that if we are going to try to find peace in the statistics wars, it has to be on terms that are going to be amenable to each warring party. Thanks.
All right, so we have no questions presently in the Q&A. Again, I would encourage you to drop your questions in there as they occur to you. William, I'm going to give you some time now to respond to Sam's comments, so take it away.
Thank you, Samuel. Tremendously useful comments, and really very much what I was hoping for. Just as a preliminary note on posting code, so our current policy is that if anyone wants a code, they can email us and we will provide it, and also the data, which will enable them to do the simulations themselves. The reason why we're doing that rather than uploading the code currently is we would like to be able to track who has the code, who has access to it, and just to make sure we get cited, basically, so that I hope this will change as this paper becomes better known, and it will just be known that if you're doing this kind of thing, you need to cite our work. So it's really just for the point of tracking citations. But I'd absolutely agree that this is important. In fact, I think that universities should change tenure policies so that posting your code and data counts the same as an article, because it really is so important. Also, I'm very grateful about the suggestion for prediction intervals, because one thing we really want to do is to make sure that in each of these simulations, we are giving each player the best possible chance and using the best possible approaches we can find for them. And we'll definitely look into prediction intervals for the frequentist. It's a really useful suggestion. I would say that, just to explain our particular choice in this case, we were following the study of Kaiberg and Teng on that choice, and they are in fact frequentists. So it's not, I think we can't be accused of being too biased. I know you weren't accusing us of doing that, but I do think that it's not ridiculous that frequentists might choose to use confidence intervals. But yeah, it will be really interesting to look at prediction intervals and see what kind of difference that makes to the results. Point on inductive behavior and inductive inference is tremendously useful. Just one point, it's to clarify, I don't think I fully clarified this, that it's not so much that we are assessing players with respect to minimizing financial losses, or even actually with maximizing financial gain. It's financial gain or payoff relative to the sample player in this paper. And we'll be evaluating that in different ways, but that doesn't really affect the point you were making, which is a really interesting one. Also, going back a step to so with the frequentist player has different estimation methods they can use. Also, the Bayesian has different priors they can use. I mentioned there very briefly the Jeffreys prior. That's a type of prior that some Bayesians are very keen on. We didn't have the time and space to investigate that in this paper, but in future papers, it'd be interesting to look at that, because it's a kind of prior that does many of the things that a flat prior is supposed to do, but it is fundamentally different prior. It essentially for this kind of problem is weighing the probability masses towards the extremes quite a bit, but still equivocally. One other qualification is that this is not a forced gamble that players have been put in. So this is one accusation, or one thing that frequentists can definitely be worried about with some of this stuff, is that Bayesianism tends to be very pro-betting, so to speak, and frequentist is more agnostic in that respect, because it isn't, well, there's a long story behind that as well, but I won't go in there. We did control for that. So it's not a forced gamble, because in one set of simulations that we detail in the paper, frequentists, at least in principle, could choose never to gamble. In practice, they always will as they get enough information in. But the frequentist player was able to withhold from betting in quite a lot of our simulations, and we found no real difference there. However, it is an important thing to look at, because in this problem, the frequentists pretty rarely withheld from betting, even when they could. It wasn't sort of something that happened often, and we tracked that. In other problems, it's quite conceivable that the frequentists will want to withhold from betting quite a lot, and thus it is important to check what happens both when the frequentist is forced to bet and isn't, because that affects the interpretation of the results. In terms of other decision problems, so there are a lot of different kinds of problems we might look at, and it's a big undertaking. We look forward to investigating these in hopefully quite a long series of papers. One suggestion that you made, Samuel, that's really good is to draw attention to the fact that we're looking here at individual behavior, and as we make our simulations more sophisticated, we can look much more at the social dimensions of decisions, which in a scientific context is really important. And it is one of the things that I'm speaking personally here, I think is attractive about some bits of frequentist methodology, is exactly things like controlling for bias in interactive scientific research, and where there are issues of trusting other people's data, trusting their selection of the data, that sort of thing. And as we make these more sophisticated, that's definitely something we should look at. In terms of other decision rules, so in this sort of exploratory study, we gave frequentists just a decision rule that we hope sort of no frequentist would say, well, that's a completely insane decision rule. But it is true that there are lots of different ways frequentists can make decisions. And as I mentioned, this is a potential confounder. In our current study, we've worked out a way where we can really make very precise like for like, so comparisons. So for example, well, for the decision rule I mentioned, which we call interval dominance, we'll actually be comparing an imprecise Bayesian, a Bayesian using imprecise probabilities, with a frequentist using interval dominance. We'll be comparing with other decision rules, like for like with that, so that differences then we can be sure are due to the update rule rather than the decision rule in the player. But I would say in this particular game, we did that to some extent. I didn't stress this in the presentation or indeed in the paper, but for example, the Williamsonian can actually be interpreted, the Williamsonian player can be interpreted also as a frequentist who just has this decision rule where they pick the action that maximizes their expected payoff with an entropy minimizing prior, with this information minimizing prior, which is, I mean, a frequentist isn't required to do that, but that's a rule that a frequentist might choose to use. It's certainly not ruled out by frequentist methodology. And they might interpret it very different from John Williamson, but it'd be the same kind of idea at the practical level. And it's interesting that we got the same feature with the Williamsonian of that they did best with this very low confidence level. So that it is possible that what was going on with the frequentist is due to randomization, but that would still leave the puzzle for the Williamsonian, whose rule doesn't have that randomizing feature. And also the sample player, again, could be, well, so that explains that. And then just also say that you can also give a kind of frequentist interpretation to the sample player that it'd be a pretty weird rule, but you could, if you're a frequentist, just choose to maximize your expected payoff with the sample frequency as a probability. But at any rate, I think the puzzle about alpha essentially remains even beyond the decision rule point, because it's there for the Williamsonian, who has a very different decision rule. But I think a lot of these things will be clarified in our future study, because our current study that we're doing, because there we are making like for like comparisons with decision rules, and I hope that will address that issue. So I'll just finish by thanking you once again, Samuel. That was very much the kind of commentary I was hoping for, and it's given me a lot of food for thought and also practical ideas about how to move forward, which is great.
All right, we have 2 questions now in the queue, and I will just read them out loud. The first is from Henry Weatherburn, and Henry asks, have you any thoughts which you can share as to the direction in which you feel that work on a meta methodology may progress?
What a question. Yes, this is actually something I've done separate research on. So I'm very much speaking now here for myself, not for my co-authors. And I'd say we cover a pretty broad spectrum of views and statistics, because I would say I'm very sympathetic towards frequentist statistics. Another of my co-authors is much more sympathetic towards Bayesian methods and everything. And my other co-author is a great example of a practical man who looks very much at the context. I think that a lot comes down to, as Samuel was saying, these methodologies having different purposes. But also a lot comes down to what we are talking about when we're talking about probability. And my own position is that once we are clear about the interpretation of probability, we can at least start to ask the question, what do we mean by a different methodology being suitable in one context or another? And so I think the interpretation of the probability and also clarifying the purposes of these methodologies will be a good direction towards developing a meta methodology.
All right, thank you. The next question is from Jeffrey Hellman. And Jeffrey asks, if one is interested in guiding degrees of confidence in scientific hypotheses, how can the frequentist even get started if the science is, for example, cosmology or the other historical sciences? Here, the Bayesian would seem to have a great advantage.
So I think I can see why you say that, because, for example, a lot of the methods in frequentism assume that you have a large sample, at least large enough to bound interesting confidence intervals, or again, with if you're interested in rejecting hypotheses, you're going to have to have a certain amount of data before you can actually reject an interesting hypothesis or not, and classify an interesting rejection problem. So I see why that can seem like an issue. As it happens, I've been talking recently with a cosmologist, well, astrophysicist, who is very critical of Bayesian methods. So it's just interesting to get people's different perspectives. But yes, within astrophysics, actually, that's where Bayesian statistics has been used for a very long time, precisely for this reason. But nonetheless, there's no free lunch in statistics or elsewhere, because, okay, you can get more interesting results with a small sample in Bayesian statistics, but that's only by using or leaning on a prior that might have nothing to do with the way the system you're studying, the physical system, let's say a star, is actually working. So you get more out with small samples using Bayesian statistics, but only by strengthening your assumptions. And I would also add that another one of my interests, econometrics, econometricians of a frequentist sort are making a lot of progress on small samples. And the trick fundamentally, to cut a long story short, is by teasing out more of what your model says about the data, you can get a more severe test with a smaller amount of data. That's a whole nother presentation, I'm afraid.
We have some time left, so again, I would encourage you to drop the questions in the Q&A. I'm going to ask one now, since we don't have anyone queued up at the moment. So I'm curious to hear more about, you drew a distinction between methodologies and decision rules. I know Sam had more to say about that. This might be more of the nature of a clarification question, but I was sort of curious if you could say more about how to parse the importance of these things within the kind of study that you were doing. I'm just not sure that I being someone who's not sort of in this literature, I'm not sure I was clear about how that would go or how that was done. So I would like to hear more.
Great, thank you. So methodology, in this context, we're mainly using it to refer to how the beliefs, or the estimates, if you prefer that term, are made as more evidence comes in. So, but just as an aside, we also use it to refer to the interpretation of what's going on here. But so that the Bayesian and the frequentists are interpreting what's happening in different ways. But in terms of the difference in the change of their beliefs or estimates, so the Bayesian's methodology is, to use a term I didn't use in the presentation, conditionalization, to adopt this conditional probability of the hypothesis on their old evidence as their new belief in that hypothesis, new degree of belief. The frequentist is using confidence interval estimation as their method. So the methodology is determining the way in which the belief has changed. Williamsonian is doing a bit of both, as I said. They are estimating a frequency and then using that frequency to bound their choice of prior probability, or of posterior probability, their degree of belief. A decision rule, on the other hand, is for a given estimate or given degree of belief, and given some opportunity to bet, by buying a ticket for heads or tails or neither, not buying a ticket at all, how do the players make a choice among those three actions, so that yeah, and the players in this study differ across all of these dimensions. Well, the frequentist and the Bayesian differ across these dimensions. The Williamsonian, actually, once they have their degree of belief, their sort of Bayesian degree of belief, they also make decisions in the same way as the Bayesian. So it's a bit of a complicated story with the decision rules and the methodologies, but fundamentally the methodologies, oh, and one last note is that the decision rules particularly from the point of view of the frequentist, are not really tied to the methodology. From the point of view of the Williamsonian and the Bayesian, it would be a very unusual Bayesian or Williamsonian who doesn't try to do this maximization methodology of maximizing their expected payoff. So there is a stronger link there. It's really with the frequentist, where being a frequentist, very roughly, it does tell you how you should make your statistical estimates in a given problem. What it doesn't tell you is what actions should you then do, and frequentists have a lot of different options there.
Thanks, that was crystal clear. Let's see. Sam, would you like to ask a question?
Yeah, I'd like to follow up on the discussion we were just having, because it highlights something that I think is really central to the big methodological question here. The big methodological question is, why should we evaluate these different methodologies by their performance in decision problems? So, there's, in this discussion with Max, we discussed how like these different methodologies have different goals, and because they have different goals, they're kind of like irreconcilable on their own terms. And so we have to find some common measure. And the choice here is figure out a way that these methodologies connect with a particular type of decision problem that serves as a common meter stick for the different methodologies. But it raises the question about whether or not the meter stick is Procrustean or not. Like, are we forcing a bunch of things into a common measuring apparatus where they were never really designed to be measured in that way? And if that's so, what exactly are we measuring? We are measuring the performance in the decision problem, but it's not altogether obvious to me then how we can separate that performance in the decision problem and say something about the methodologies, except insofar as the methodologies are then used to determine the decision procedure. Does that make sense, William?
Yeah, it does. It's definitely true to say that the methodologies have different goals. And you highlighted this very well in your commentary, that with the Bayesian approach, for example, there's all this talk about rational beliefs and degrees of belief. Frequentists can talk in that way, and some of them do, but most of the time don't. And it's definitely not fundamentally tied into their methodology. However, I do think that there is crossover of goals, so that given that statistical results are used in practical decisions within science, for one thing, in terms of what science to fund, but also, of course, within policy, within our everyday lives, our everyday choices, we're using statistical information. I do think it is quite a good common ground to look at for that reason, that it's not that frequentists are uninterested in making good decisions with statistical information. They may not analyze statistical methodology all the time in those terms. So some Bayesians really would say, forget all the stuff about degrees of belief or estimation. It's all about making the right choices. And even one or two frequentists might talk that way. But even for those of us who don't find that way of thinking about statistics persuasive, to think that decision making is the be all and end all, and I'm definitely not of that view. Nonetheless, that's one of the reasons why we value statistics in science and in our lives and in policy, so that as a way of finding some common ground to look at, it's quite useful. I have to say just briefly on the issue of whether or not this should be viewed as making peace or a battle. So we take the statistics wars metaphor from Deborah Mayo. I think particularly light of some recent events, I'm not tremendously keen on the metaphor myself. And the title of this talk in some respects is a move towards phasing out the statistics wars methodology, I hope. Not just in terms of, well, unfortunately it is the case that wars are often won by winning, or often made peace out of them by the winning of battles, but also in our research thus far, we have been holding up players quite oppositionally. What would be interesting to do, perhaps this is many steps into the future, but what would be interesting to do, for example, would be to look at, well, what happens if you have different mixes of populations of different sorts of researchers? Is there a gain in diversity among statistical methodologies in some of these simulation problems where, for example, if we have a sort of imaginary community of scientists voting and they're using different methodologies, is there an advantage that they can perhaps a more pluralistic scientific community might avoid certain kinds of problems, or maybe not, maybe there just really doesn't matter what the composition of the population is. The great thing about these simulations, I think, is that we have no idea what's going to happen in them. We really had no idea what was going to happen with this study. We knew about this early study by Kaiberg and Teng, where they got one result, but with their computing power, I suspect it just wasn't possible to rule out random error as an explanation of many of their results. So we just didn't know what's going to happen. We don't know what's going to happen in the current study we're doing. We don't know what's going to happen in these variations that we've been talking about and other variations we can do. It's tremendously exciting. I suppose it's about the closest philosophers get to experiencing some of the excitement of being a proper scientist, where you don't know what's going to happen in the experiment, and that's the joy of it. Hopefully we'll be able to focus on problems where that's not predictable, because sometimes in simulations you can actually work out what's going to happen. It's not in science that very rarely happens. In philosophy, sometimes you can specify a model and you actually know what the result is going to be, even though someone who's unfamiliar with that model, it might not be obvious. With this type of model and these sorts of players where there are so many random factors involved and where formal proofs of what's going to happen are difficult, if not impossible, it's an exciting jump into the unknown.
Well, we have about 5 minutes left if there are other questions. Or if, Sam, I don't know if you want to ask any other follow-up things that would be appropriate. I suppose I have one other question, which again comes out of my ignorance of this literature. So the project of providing a kind of irenic account between these different interpretations of statistics, is that a sort of ongoing area of inquiry? Are other people doing this sort of work? And if so, I assume they're not using simulation methods. They're doing something rather different.
No. So I'll just give two examples I've mentioned, two examples of philosophers who've been trying to take an ironic approach. One of whom, Henry Kaiberg, who I've mentioned several times, unfortunately is no longer with us, but was one of the early figures in philosophy to really engage with what statisticians were doing. And he was even in correspondence with Ronald Fisher in the 1960s about really trying to work out what are the statisticians thinking, how can this be interpreted philosophically. So he was there in the very early days. Now his view was later picked up by John Williamson, who I've talked a lot about in this presentation. John Williamson, just to give an example of someone who's taking an ironic approach, to sum up his view in a nutshell, it implies that in case, when you're doing what he calls calibrating, which is working out an estimate to guide your choice of degree of belief, an estimate of relative frequency, you should use frequentist statistics where your background knowledge is weak, but Bayesian statistics where your background knowledge is strong. And that's because he says that these Bayesian priors, they do have a role, but they should be where, for example, we have some, let's say, model from theoretical physics that gives us some good idea about how some stochastic system is going to work. So when you can do that, fine, Bayesian statistics has a big role. But when you can't determine a prior in that way, what can you then fall back on? Well, the great thing about a lot of these frequentist methods is they do have these long-run performance results, and the long run isn't everything, but if that's what you have to go on, maybe that's a good guide. He's not really addressed, just to mention one other name. So John Norton has not really addressed statistical inference head on, but I think a very similar view follows from his theory of inductive inference, where it's your knowledge of your sort of target system that determines what inductive methods are appropriate or not. And I at least have argued in some papers that if you take that view, frequentist style statistics has a sort of fundamental role, because you might not know much about the target system, but if you know you have a large sample of it, for example, that enables you to infer certain things about particular statistical tests. And if that's what you have to go on, that's what you should use. So yes, there's a lot of work on this, and it's a very exciting area of philosophy, I think.
I'm going to end with a comment. Henry Weatherburn dropped something into the Q&A. He says, our aim is to use the quote unquote best statistical test in the medical field. And for clinical trials, looking at survival, we use a frequentist approach, but for blood tests, a Bayesian approach. All right, so we are at 1:45, almost on the nose. So thank you again, William, for a wonderful talk, and Sam for a very enlightening commentary. And thank you all for coming. Hopefully we'll see you again at future installments of this postdoctoral forum. Bye.
Thank you very much. Goodbye.